Okay, so I am almost done grading all of the exam twos. I have a few left to grade, and then I will release those grades. They're hidden right now, but I'll have those done so that you could start working on the exam. If you want to make up any points, you could start working on that. Um, so I'm hoping to have that done by today. Um, the exam 3 review, I'm hoping to have out. I'm not sure. I guess by tomorrow night. Yeah, I guess by tomorrow night so that we can talk about the exam review on Wednesday's lecture. So exam 3 is going to be next week. I think I'll probably keep so the due date was going to be Friday of next week, but I think I'll just move it till Sunday night instead. So it'll be open on Monday and then due on Sunday of next week. So not this coming Sunday, but the next Sunday. Homework 8 will be available sometime, hopefully today. I'm working on getting that done as well. I'm a bit backlogged in my grading, so just be patient with me while I get things graded. So I think that's all I have to say there. So I wanted to do a few more of the optimization problems. I wanted to do, I think, 2 more optimization problems, and then we can move on to antiderivatives, which will be the last section in this unit. And then we're moving on to unit 4, which is the last unit in the class. So we're almost there. So I wasn't originally going to do this problem, but we're going to do this problem. It's a fun one. So let's read this problem. It's an optimization problem. Upon imposing a coordinate system, a bug is traveling along the curve f of x equals the square root of x minus 8, and a chameleon is standing on the point 12, 0. Find the closest point on the bug's trajectory to the chameleon so that the chameleon has the best chance of catching it with his tongue. So there's a lot here. Let's kind of work through it. That's the whole point of these, is to look at it, maybe feel a little confused at first, but work through it. So we know that there's a bug traveling along the curve, the square root of x minus 8. And maybe we remember some stuff from Math 126 with regards to graphing. Move that a little bit. So the graph of the square root of x minus 8 is going to be the square root graph, but it's been shifted to the right by 8 units. So this is the graph of f of x equals the square root of x minus 8. This is a shifted graph. A chameleon is standing on the point 12, 0. So the point 12, 0 would be this point right here. This is where the chameleon is standing. Oops, let's not spell chameleon wrong. We want to find the closest point on the bug's trajectory. So the bug is traveling on this. There's a chameleon here. This is the bug's trajectory. To the chameleon so that the chameleon has the best chance of catching it with its tongue. So we want to find the place on here where the bug is closest to the chameleon. Let's not use the word place. Let's use the word point. We don't know exactly where that point's going to be. You know, we can make a kind of guess right here, like somewhere in this area. One thing we can do is we can write down the coordinate points of this point. I don't know exactly what this point is, right? But I know that there's some x value down here between 8 and 12, maybe greater than 12, doesn't matter. There's some x value in general where this distance right here is minimized. And this coordinate point has the x value x and the y value square root of x minus 8 because it's on the curve square root of x minus 8. And we are minimizing this distance here. We want to find the minimum, we want to find the point that has the minimum distance between the point 12, 0 and some point on this curve. So this requires knowing the distance formula. So I'm going to call this distance right here d, the distance between those 2 points. In general, the distance formula, the distance between 2 points, and I'll just use general points right here, like x1, y1, and x2, y2, this is the distance formula. You should have learned this in Math 126. It's the square root of the quantity x1 minus x2 squared, or x2 minus x1 is typically how it's written. It doesn't matter. It'll be the same either way because it's squared, plus y2 minus y1 squared. So that is the distance formula. And the distance formula is what we are trying to minimize. Now, we talked about there being an optimizing equation and a constraint equation. And the constraint equation in this case ends up just being the fact that the constraint is that the bug is walking on this line. This line right here is the constraint that the bug has. You're trying to minimize this distance with the constraint that the bug only is walking on this curve. He's not walking out here, he's not walking in here, he's not walking down below here, he's only walking on this curve. But we're trying to optimize, we're trying to minimize this distance function. So we're minimizing this function d, and we have values for these x1, y1, x2, y2 points right here. Right? We can call this guy x2, y2, x1, y1. So x2 is x minus x1 is 12, quantity squared. I'm just plugging in these values to this distance equation, which is what we're minimizing. Plus y2 is the square root of x minus 8 minus y1, which is 0. So this last part over here, this is just going to end up being the square root of x minus 8 squared. And if you square a square root, you just end up with x minus 8 there. Over here, this part right here would need to be FOILed. So foiling x minus 12 squared, we have x squared minus 24x plus 144. That would come from that very first one being FOILed out. And then the second one, like we said, would turn into x minus 8. Let's simplify this first. So this would be x squared. We have minus 24x plus x. So that's going to be minus 23x. 144 minus 8 is going to give us 136. And then there's two things we can do here. So one option you have here is minimizing distance. This is kind of a trick. Minimizing distance is the same thing as minimizing the square of the distance. So you can square both sides of this and just minimize that function. That will work. And it ends up being a lot easier. But you could also just take the derivative of this guy the way that he looks. So that you could take this derivative, you would put him in parentheses, raise it to the 1/2 power. And then, you would do power and chain rule. But it's a little easier and a little more fun trickery to minimize the square of the distance. Because if you square the distance, you're just going to end up having a polynomial that we can take the derivative of really easily. So this is a common trick people use, is you'll get the same x values if you minimize distance squared. So something to note, oftentimes we denote if we're going to use distance squared, because this happens frequently enough. If we use the distance squared function, instead of writing d squared, because we don't really want to talk about it as d squared, we want to talk about it as brand new function. The function is distance squared. We put it as a subscript instead of a superscript so that it doesn't look like a square. So the distance squared function is the same thing as d sub 2. So that is the same thing as squaring both sides here, but we're not writing it as a square because we're not here to do implicit differentiation. We're just here to use an easier function. So if you square a square root, this is just going to get rid of the square root. From here, we can take the derivative. So we get 2x minus 23. We set it equal to 0. You're going to get x equal to 23 over 2, which is 11.5. At this time, we have what is hopefully the x value. So the x value right here is hopefully 11.5. But we want to double check that this gives us a minimum because we're trying to minimize the distance between 2 points. So we need to be sure that this gives us a medium. So this is not an optional step right here. This step, if you don't do this step, you will be marked down points on the test. You need to check that you are actually at a minimum and not like a maximum. The easiest way to check for a minimum is to, in many cases, not all cases, but in many cases with the optimization problems, the easiest way is the second derivative test. So you find the second derivative. If you take the derivative of 2x minus 23, you get just 2. 2 is greater than 0, which means that you are concave up. And if you are concave up, you have a minimum. That's all the checking has to be. It's not a lot of work. It's just double checking that the concavity there is positive would give you a minimum. If it's negative, you'd be concave down, and that would give you a maximum. So then the point we're looking for, right? It was x comma square root of x minus 8. X is 11.5. This would be the square root of 11.5 minus 8. So one of the questions, in the chat is, so we aren't looking for a minimum or maximum specifically. It can be either. It all depends on the problem. So in this particular problem, we were told that we want to find the closest point on the bug's trajectory, which means we wanted the distance to be minimized. So it's all about looking for the context in the problem that you're doing. So for example, on the previous problem that we did last week, we were looking for like this one here needed to have the box holding as much as possible. So holding as much as possible was maximizing. So when we did our verification down here, we wanted it to be concave down so that we got a max. So it depends on what the problem is asking for. If it's looking for a min, you need to verify it's a min. And if it's asking for a max, you need to verify it's a max. Does that make sense? No problem. Oops, there we go. So oftentimes we give like rounded answers because these problems are asking for like feet or something, like they're asking for something that's best measured in decimals and approximations as opposed to exact answers. In a problem like this where like you're looking at a graph, it's okay to leave it as an exact answer. But if you did round it, since we did say that we were rounding at the very beginning of the section, we said we round all of our answers to 2 decimals. This would be the rounded answer. On a test, I would be very specific about whether I want rounded or not. So this is not an exact, this one's an exact answer. And this is our rounded answer. In this case, this is more appropriate, but like once again, most problems would be very specific about what it's looking for. Any questions on this problem? Okay. If you're typing, feel free to keep typing. Because we do need to get to a different section today, I just want to do one more. I want to do one additional problem that has a slightly different setup so that we can talk about it. So a small luxury chair company is trying to prepare for the holiday shopping. Their Voodoo Accountant determines so here's the story behind the word voodoo here. In business calculus, you end up with a lot of these situations that are perfectly modeled by functions, where in a real business situation, you can't have a perfect modeling of what your revenue is going to look like. So when it says their Voodoo Accountant, they just mean that it's like this accountant has powers beyond what you could possibly believe because they're able to perfectly, with a nice polynomial, model what their revenue should be. So their accountant determines that the revenue of their chairs can be modeled by the function R of q equals negative q cubed plus 60q squared plus 1500q, where R is measured in dollars and Q is measured in luxury chairs. So Q is for quantity. It's the quantity of luxury chairs. Due to their size, they can produce at most 70 chairs. This is important. This at most 70 chairs part is incredibly important, and it changes the way you do the problem entirely. So it's really, really important that you make note when there's restrictions on the domain. So right now they're telling you that Q can't be more than 70. There's restrictions. There's at most 70 chairs that they can produce. And it says how many chairs should they produce to maximize their revenue. So there's a domain restriction. And like I said, we need to make note of that, and it's very important. So for Q, it said that the most that they can produce is 70 chairs. But there's also a least amount that they can produce. So they can't produce negative chairs, right? They can't go and steal chairs from their customers and then say that these are our chairs that we're selling. So they can't have negative chairs, but they could indeed produce 0 chairs. Is it a good company model to produce 0 chairs? Probably not. But you could indeed produce 70 chairs. 0 chairs. 0 chairs. You could produce 0 chairs if you really wanted to. So the domain of Q is between 0 and 70. What we want to do is maximize revenue. And the function for revenue has been given to us. It was given to us right here, R of Q. So we want to maximize this function. So we're going to take the derivative, set it equal to 0, find our critical values, just like we have done. So we didn't have to set up anything in this problem. The setup is basically all there for you. So we take the derivative, we have negative 3q squared plus 60q plus 1500. We're setting it equal to 0. We can factor out a negative 3. We would get q squared minus 20q. Did I not do something here? Yeah. Da, da, da. I'm sure somebody's typing a comment right now. If not, should have caught that. I didn't take the derivative here. 2 times 60 is 120. 120q plus 1500. So this would be minus 40q. So make sure you fix that. This should be 120q. Minus 40q minus 1500 divided by negative 3. That's going to be 500. Equal to 0. And this factors into q plus 10 times q minus 50, which gives you the q values, negative 10 and 50. Right away, we can say, well, we already talked about this domain restriction. We can't have a negative number of chairs, so this one gets thrown out. So then we would normally be like, okay, now we can just do the second derivative test and see that this is our answer. But that's actually not what that's not what we do here. We're not going to verify this using that test. The difference here is that we are on a closed interval. What that means is that the way that our graph looks, it could look, let's see. It could look like this. Like, what if 70 was here? This is revenue. And what if this was 50? Because let's pretend that that scale made sense. So 50 could have a maximum here, right? This is a local max. This is not necessarily what this graph looks like. This is just me trying to explain what could happen. This is a local max, but that maximum there isn't more than the revenue you would make by selling 70 chairs. So it's possible to have local maxes, but not have them be bigger than the endpoints. And it's possible that selling 0 chairs would potentially get you more money than making any chairs at all. If you have a really bad business model, you might make more money by doing nothing. So it's important because you don't know if this is a local, first of all, we don't even know that this is a local max. This could end up being a local min, right? This could be a local min. And we don't know which of these Y values is biggest because we want the Y value to be biggest. So instead, we have to treat this like absolute extrema. So we have to take all of our values that are within our domain and then our endpoints of our domain and plug them back into the original equation to look for the absolute max. And this is what you do when you're on a closed interval. So because we're on a closed interval, we're looking for the absolute max. So which means we need to plug all critical values that are within the interval. So that one was 50 was the only one, back into the original equation. And that's the original, not the derivative, along with both endpoints of the interval. So we were on the interval 0 to 70. The critical value we found that fit within our range was 50. So we need to check 0, 70, and 50 back in the original equation, which was R of Q equal to negative Q cubed plus 60Q squared. This is the original, not the derivative, plus 1500Q. So when you're doing these absolute extrema problems, you are plugging back into the original equation to find out the biggest Y value. Let's use blue. So if we do R of 0, plugging 0 in, negative 0 cubed plus 60 times 0 squared plus 1500 times 0. If you make 0 chairs, you make $0. Excellent. If we plug in 50, we get negative 50 cubed plus 60 times 50 squared plus 1500 times 50. And if I'm correct, this should give you 100,000, but maybe I'll just double check it. Yes, gives you 100,000. And then R of 70 would be negative 70 cubed plus 60 times 70 squared plus 1500 times 70, which should give you 56,000. Again, I'm going to double check it because I'm going off of what my notes have for those numbers. Yeah, 56,000. So then you're picking the biggest one because we're looking for maximums. So this guy right here, this is the maximum. So they should make 50 chairs because 50 was where the maximum happened. Now, there's a few things here. You don't have to verify the max when you're doing a problem like this. The verification of a max happens right here. So there's no looking for concavity. All you have to do is just plug in the endpoints and then the critical values within the interval, look for the biggest one, and that's going to be your answer. So you don't have to worry about the second derivative here. That's one thing to say. The other is it's really important that you recognize when you're in a scenario where you are on a closed interval and you recognize how they are treated differently. Because when you are on an open interval, so for instance, this guy here, it's like a half open interval, but you had until infinity, right? This thing goes off infinitely. On the box problem, we had open intervals because you couldn't cut out 0 inches from the corners and you couldn't cut out 10 inches from the corners. So you had open intervals here. With these open intervals, there's no, you're just looking for the critical values, then using the second derivative to double check for max or min. With a closed interval like this, which typically happens, a lot of business problems will have this, you do need to check those endpoints because it can happen at the endpoint. Something interesting. Back when I was teaching business calculus at Ohio State, my math lab was the program they were using, and my math lab was a little bit broken on this particular type of problem. So this problem, the program was so broken that if you had a problem like this and the maximum did occur at an endpoint, it wouldn't accept the endpoint as an answer, even though that was exactly what the problem was trying to teach you. The problem was trying to teach you to check your endpoints. But the programming for the problem forgot to check the endpoints, so it was always the number in the middle. So that was funny. That happened for many semesters. They never fixed it. But it's not always true that it happens at the middle one. It's not always true that it happens at the critical value. Sometimes it'll happen at the endpoints. And what I had to tell my students back then was, hey, so you're going to do this problem and you're going to have to submit this value as the answer. But on the test, you're going to be marked wrong if you do that. So make sure that you actually are identifying which of those are the minimums and maximums by plugging in those original endpoints. So I think that's all about optimization that I have to say. Are there any questions on optimization before we move on to the next section, which is a nice, it's a dive in a completely different direction. I'll give you a moment just so you can type anything you're typing. So here's the fun part of teaching calculus on a semester system. Calculus is typically broken up into 3 chunks. On a quarter system, this works, like on a quarter system, calculus is broken up into 3 chunks, where you'd have Calc 1, which would be derivatives, Calc 2, which would be integrals, and Calc 3, which would be multivariable. So this would be on a quarter system. This works out really, really nicely. Because in a quarter system, I know we don't have those here. On a quarter system, you have 3 quarters in a year, essentially, because summer quarter is the 4th quarter, but not everyone goes for summer school. So you have your fall, winter, spring. And this breaks up nicely because derivatives and integrals are actually the opposite of one another. So the way that you have to think for integrals is opposite the way that you have to think for derivatives. So you learn derivatives first, then you take a break, and then you learn about integrals. And in a whole brand new semester, you learn about integrals, and you kind of have to unlearn the way that you learn derivatives so that you're able to learn integrals. Unfortunately, we are not on a quarter system, and instead we are on a semester system. So the way that the calculus breaks up here is like this, where half of the integral stuff goes into the first semester and the other half of the integral stuff will go into the second semester. So what we're about to do with the next section, we're not going to do differentials, by the way. I know 3.6 is differentials. We're skipping differentials. We're going to 3.7, which is antiderivatives. Antiderivatives are the beginning of integrals, and we are about to undo the way that we think about derivatives. This is going to be an uncomfortable change. Your brain is not going to be happy at first. It's not an ideal way to learn calculus, but it is the way that we have to because of the way the material gets split up on a semester system. So I'm just trying to warn you, not scare you. Your brain will adapt, but at first you're going to be a little uncomfortable because you're going to have to think about integrals, which are the backwards direction of derivatives, essentially. And at the same time, during the final, you'll need to be able to do derivatives, right? So you'll need to be able to do derivatives and integrals at the same time, but one is kind of the opposite of the other. So just a kind of warning about how things are about to look. So I'm going to skip, I'm skipping differentials. We are skipping the entire section of differentials. It's not a very important section. There's some motivation for why you should care, but it's something you get in Math 182, and it's fine. You'll be fine skipping them. When I when I learned differentials, the section that we're skipping, my teacher was like, so I feel like this is kind of like hazing. Like, we teach you this, but there's no reason for us to teach you this, but we teach you it because we had to learn it. So here it is. Differentials are really not that useful. They have like very abstract connections to other things in math, but not enough for me to want to spend time on it. So we're skipping that. We're going to spend more time on antiderivatives instead. You guys will be okay. It'll be fine. I promise. It's going to be fine. It just takes some getting used to. So here's the big thing with antiderivatives. The thing with antiderivatives is, hey, if I have a derivative, if I have a derivative, can I find the original function? If I have a derivative, can I find the original function? So, for example, like if I have a regular function, like taking the derivative of this, right? If we take the derivative, we get 3x squared plus 4x plus 1, right? But now pretend we don't know this information and we want to find out what derivative what we took a derivative of to get this. We have this, but we want to know what happened from the step before this to get here. That's what we're going to figure out. How can we go in this reverse direction here? How can I take a derivative and go back to my original function? So starting with the derivative, moving backwards. Now here's fun, interesting thing. In general, there's not one easy answer to this. So the function I gave you to get to that derivative, I said the function was x cubed plus 2x squared plus x, right? That this function gave you this derivative, which is totally true, totally did. However, that's not the only function that will do that. Yeah, you need to have this x cubed plus 2x squared plus x part, but I could have a plus 7 here. Because if I took this derivative, I would still get what I have right here, right? The 7 would disappear. X turns to 1, 4x, 3x squared. There's infinitely many combinations you can have because I could add any constant at the end here, and that constant will give me the same derivative. So that's the fun thing about what we're calling antiderivatives. So antiderivatives are, what's the function that gave me this derivative? What's the function that gave me this derivative is what an antiderivative is. So if you have a function, capital F, we typically use capital F's for antiderivatives. If you have capital F, it's an antiderivative of the function f if, when you take that antiderivative's derivative, you get the original function back. So the relationship that baby f and big F have, f is the antiderivative of f if when you take his derivative, it gives you f, baby f. So f, baby f, is the derivative of big F, and big F is the antiderivative of baby F. So they have this reverse relationship to one another. Now, here, this is going to end up saying what I tried to say over here. In fact, it used like almost the exact same function. I wasn't even looking over here. Almost the exact same function, not exactly the same. But so for instance, this function here is an antiderivative of this function because if you take his derivative, it would give you this function. So it's really not 100% right to say the antiderivative. It's more appropriate to say an antiderivative because there's multiple functions that you could use that would give you this as the derivative. Just like I was saying over here, there's multiple functions you can use that are antiderivatives of this derivative. So oftentimes what we do, instead of saying that this is the only antiderivative, which it's not, right? We could add any number at the end here. Since we know we can add a number at the end and we can add any number at the end and it will still be an antiderivative, what we end up doing is saying, okay, well, plus c, where c is just some constant. Any constant you want, you could add at the end and it would still be an antiderivative. Because when you take the derivative of a constant, it turns into 0. So technically, we call f of x plus c the general antiderivative when we do this plus c here, but general just becomes assumed when discussing antiderivatives. So always when we're talking about antiderivatives, we're putting this plus c here. This is something that I'm going to drill into you for the rest of the semester. This plus c thing will become so important and something that you hear so many times. You'll get sick of me saying it, but that doesn't matter. I'm going to continue saying it. The plus c is really important because otherwise you're saying that this is the only function whose derivative you can take to get this guy right here. And that's not the case. You could add any constant at the end and it changes it. So we're going to do some examples where we're finding antiderivatives. We're going to be asking ourselves here the question, what do I need to take the derivative of to get x squared? Right? What do I need to take the derivative of to get x squared? We know that we could put a constant at the end, so I can just put the plus c there. That's fine. And I know that if my exponent became a 2, in the derivative. So remember, these guys over here, you're looking at, these are the derivatives. These over here are going to be the original functions. We know that this guy had to have an x cubed on him, right? Because in order for this to become a 2, this would have to be a 3 to begin with, right? This would have to be a 3 so that when he comes down, he lowers his power, he becomes a 2. But then we want the coefficient in front to be 1. We want that coefficient in front to be 1. And if we took the derivative right now of what I have written, this would become 3x squared. That derivative would become 3x squared. But that's not what we want. We don't want 3x squared. We want it to just be a 1. So what could I put in front of the x cubed to make it so that when I bring the 3 down, it turns into a 1? What could I put in front of the x cubed? 1/3. I heard 1/3. That would be correct. 1/3. Excellent work. Yeah, so I could put a 1/3 in front, and I can erase this here. Let's do it in black. I could put a 1/3 in front, and then bam, when I take that derivative, you get 3 over 3 cancels, you get x squared. So if you take the derivative of 1/3 x cubed plus c, you get x squared. Therefore, 1/3 x cubed plus c is the antiderivative. So you can say it's the antiderivative when you have that plus c there because it covers all antiderivatives. That is the antiderivative of x squared. So looking here, there's some more fun ones on the next page. A lot of these ones here are not going to be as problem-solving. I'm going to skip 1 over x for a moment. E to the x. If you think about the function whose derivative you need to take in order to get e to the x, well, e to the x gives you e to the x, right? You take the derivative of e to the x, you get e to the x. So the antiderivative of e to the x is e to the x plus c, because you could have e to the x plus 2, and his derivative would be e to the x. I'm going to skip this guy. I'm going to skip this guy for a moment. I'll come back to it. Here, the derivative secant tangent. If the derivative, once again, these guys over here are the derivatives. These are going to be the original functions. If the derivative is secant tangent, the trig function that gives us that derivative is secant. Secant's derivative is secant tangent. So secant x plus c is the antiderivative of secant tangent. The next two are inverse trigs. So I know that the inverse trig that gives me this derivative, 1 over the square root of 1 minus x squared, that one is sine inverse. Sine inverse has that derivative. And tan inverse has this derivative. So then we have some fun stuff to deal with. There's a few spots left to talk about fun stuff. Now, there's something special with 1 over x. So first of all, power rule wise, there's something important there, because like if you tried to do power rule, like if you tried to do like a reverse power rule on it, you're going to get like x to the 0. It's going to be weird. But if you remember logarithms, logarithms give you this derivative, right? So like the derivative of ln x would be 1 over x. But there's actually something very special about the antiderivative of ln, of 1 over x. The antiderivative of 1 over x is not ln x. It's ln of absolute value of x. It's ln of absolute value of x. And I'm going to make some notes down here about that, about why that's the case, because there's no reason for you to think that without having a little bit more explanation. So the reason we use the absolute value here is because of this. In the forward direction, you start with f of x equals ln x, right? No absolute values. And you take its derivative and you get f prime of x is equal to 1 over x. Now, in the forward direction, the domain that you began with already had, this domain is limited, right? This domain is limited because ln has a limited domain. So the domain of your original, the domain of where you started, is from 0 to infinity because ln's have a domain of 0 to infinity. So when you take the derivative, it uses the same domain. Now, if we're looking in the backward direction, if we're starting with we're starting with the derivative, we're moving to the antiderivative. So we start with 1 over x. If you start with 1 over x, his domain, the only number that's not included is 0, right? The domain would be from negative infinity to 0, union 0 to infinity. So 0 is the only number not included. Now, it would make sense, like, this function should have an antiderivative for this portion out here as well, right? This negative portion. But if our antiderivative was just ln x, like this, we should, I could do plus c here, but I'll just write ln x. I'll put a plus c, you know what, for good notation. If it were no absolute value here, it would be taking in all these negative values and it wouldn't be able to do anything with them because these negative values aren't in the domain of ln. It can't take in a negative value. It's good that it excluded 0 because 0 it can't take in either, but it can't take in any of these negative values. But that doesn't mean that there's not an antiderivative for if this part was negative. So to take care of that problem, we do an absolute value of x to make it so that if you have a negative number in the derivative, that it just turns positive in the antiderivative. Someone in the chat says, so you need the absolute value to keep the x positive. Yes, absolutely you do. Absolutely. Just give me a chuckle on that one. Yes, so to keep the number positive on the inside, we use those absolute values. So this is something that I'm going to be hard on. Just like this plus c thing, the absolute value part, when you're going in the, and this is important, when you're going in the antiderivative direction is important. When you take the antiderivative of 1 over x, you're going to have absolute value of ln, ln of absolute value x, that is. So that's one of the ones I wanted to point out here. For these last two down here, for cosine x, what do we take the derivative of in order to get cosine x? I guess this one's not as bad as what this one will be, but normally it's important to think here because your brain is going to get really frustrated with cosine and sine. All right, it's going to get really frustrated because of the negatives. So cosine's derivative is negative sine. His derivative is negative sine. But the function you take a derivative of in order to get cosine is positive sine, right? Sine of x, his derivative is positive cosine. Sine's derivative is positive cosine. So cosine's antiderivative is positive sine. Now let's talk about sine 2x. We need to take the derivative of something and get sine of 2x. Now we know that it has to be a cosine of some sort, right? And it's going to have a cosine 2x involved in it, right? We know that the inside, if we take the derivative, like chain rule makes the inside stay the same, right? So we know that the inside would stay the same. And we know it has to be cosine because cosine's the only one who would give us sine. But then there's the problem of the fact that there's nothing here in front of the sine, right? Because if I took the derivative, just the flat out derivative of, if I took d dx of cosine of 2x plus c, this would give us negative 2 sine 2x. It would give us negative 2 sine 2x. The derivative of cosine of 2x would be negative because cosine's derivative is negative. And then 2, because of chain rule, sine 2x. Negative 2 sine 2x. Okay. So if we want this to instead be just positive sine, we need to make this negative 2 go away. What could we do to make that negative 2 go away? What could we do to make negative 2 go away? I hear a negative 1/2. Yeah, so it would have to be negative because you want the negatives to cancel, right? We want it to become positive. And then 1/2 would get rid of the 2. So if it were negative 1/2, the 2 would come out, right? Cosine's derivative would become negative, so 2 negatives make a positive. The 2's would cancel. You'd get positive sine 2x. Now, we are going to get rules. We are going to get rules that allow us to talk about these faster than kind of problem solving, but I think the best way to learn antiderivatives is to go through a bit of a problem solving process to see how they're formed in the first place. Because the connection is there and you have all the pieces. It's just about putting them together backwards from how you've put it together all semester. Oh, and I think in the chat here, I missed a comment in the chat. Or did I miss a comment in the chat? That we wanted always to be 1. I'm wondering if that one came from here. Just noticing that. So I think that somebody at this point right here had commented that we want it to always, like, do we want it to always be 1? We wanted it to be 1 in this case here, and in this case here, and then in this case here, because that was just, that's what this table is filling out. Now, if my question was, how would I get 1/2 x squared? That would be different. So it's just about that this one was given to us and there was a secret 1 in front. So it just had to do with the particular function we were working with. It's not always a 1. And I think on this next page, you'll see some situations where it's not a 1. So I kind of want to work through some of these. Some of these. So looking at antiderivatives here, which ones do I want you guys to look through? Let's start with looking at these 4 here. I want you to do a tiny bit of thinking on these top 4 about what you would take a derivative in order to get this. And again, I suggest the way that you go about this, because I'm going to pause it and give you guys time to think. I suggest the way that you go about this is thinking about, for these guys, maybe thinking about what the powers would need to be. And then for some of them, you're going to need to think about what chain rule would need to be. And you kind of work your way backwards. So once you have a general idea of what the antiderivative should be, right, then you'll take that derivative and say, okay, now I want the numbers to line up. So what do I need to do to make the numbers line up? So mess around with it a little bit. Give your brain a moment to just kind of mess with it. And I will give you answers, but I'm going to give you a second to think about this. I think I'll give you let's say like 6 minutes or so, just to kind of look at these. Get as many of these done as you can. You can look at your derivative charts for what the derivatives were to get an idea of what some of these might be. But mess around with them for a second. All right, so my timer just went off, so let's start working on these top 4. So looking at these guys, we can figure out what the powers are going to be, right? We know that we have to have like an x to the 4th, and we know that there's going to be, this has to have a minus sign in front of it, right? And this would have to be an x squared. So then it's a matter of filling in the blanks of like what goes in front, and then we also have a plus c. So let me erase those. So we have a plus c. So we have to figure out what goes here and what goes here. Now, if we were to just take the derivative of x to the 4th minus x squared, we would get 4x cubed minus 2x squared. Not x squared, 2x. But we don't want that. We don't want this to be a 4. We want this to be a 3. Not a 3. We want this to be a 12. So if we wanted this to be a 12, we would need to have a 3 in front of here so that when we took the derivative, 4 times 3 would give us 12. Here, we want this to be a 5. So it is a negative 2. We want it to become a 5. This one's a little trickier. What number can we put here so that when it comes down, and when it gets multiplied by 2, it becomes 5? What number, when it comes down, what number multiplied by 2 gives us 5? I hear a 5 halves. I hear a 5 halves. Yeah, so 5 halves. Oops, draw. 5 halves. Right? Because 5 halves times 2 gives you 5. So that would be the antiderivative for that first one. The antiderivative for the next one's not so bad. So the function whose antiderivative is, now we're going to get to the point where I'm going to get tongue-tied because I'm going to say antiderivative when I mean to say derivative. So we're just all going to get tongue-tied here. The function whose derivative is secant squared is who? Who has the derivative secant squared? I hear tangent. Yeah, so it'd be tangent x and then plus c. Tangent. Start getting a little trickier. Okay, well, looking at this guy here, assuming chain rule happened, we know that there would be a 5x minus 9 raised to the 8th plus c, right? Obviously, something is going to need to happen out front here if we want there to not be anything out front, because if we took the derivative of this, you'd get 8 5x minus 9 to the 7th, and then chain rule, the derivative of the inside would be 5. So this would give you 40 5x minus 9 to the 7th. We don't want it to be a 40, we want it to be a 1. So in order for this 40 to not be there, we would have to have a 1 over 40 in front. You'd have to have a 1 over 40 in front. Because otherwise, when you take, the derivative, you're going to get that 40 in front there. So to undo that, we would have 1 over 40. For this next one here, this looks a lot like tan inverse, right? We know that tan inverse of x, he has the derivative 1 over 1 plus x squared. So it looks like it should be that. Now we have, options of what could happen here. If we wanted it to be -7 on top, there's two ways you could do this. The first one, if you just put a -7 out front, that would work, right? Because if you multiply this by -7, then you get -7 over 1 plus x squared. But you could additionally do something else. And did anyone else get a different answer on this one? For it's a tan inverse, but did anyone else get something slightly different? It's okay if you didn't, but just wondering if anyone else saw something potentially different that could happen. So what if you had, oh no, just kidding, this next one wouldn't work. Just kidding. I was really excited for a second. I was like, oh, this would totally work if you had -7x, but my brain doesn't work so well. So I'll tell you why this one doesn't work, because my brain was thinking it would work. If my brain was thinking it would work, I have no reason to believe that anybody else would not think it would work. So my brain was thinking, oh, you could totally have done this. We could have done -7, because then chain rule would have put the -7 up top, but this won't work, and I'll show you why. This won't work because you would have the 1 over 1 plus, and then you would have to do -7x squared, and then multiply by the derivative of the inside is -7. So you would get the -7 on top, but you would also have 1 plus 49x squared on bottom, so that wouldn't work. I was really excited for a moment, but that won't work at all. But it's fun to talk about why my brain might think that it would, or why your brain might think that it would. So the only one that would work here, this guy here. I know I didn't tell you to work on these bottom ones, but let's go ahead and go through these. So the one for cosecant, cotangent, we know that cosecant has the derivative negative cosecant cotangent. So if we want our derivative to be positive, if we want to take this derivative and be positive, we would just put a negative in front. So negative cosecant, cosecant, his derivative would be negative, so cancel to be positive, and then negative cosecant x plus cotangent, or not plus cotangent, times cotangent. For 2x squared times e to the x cubed, you know with e to the x that the e to the x cubed part always, like the exponent and the e part, end up in the answer, right? So if we were to look at that and take that derivative, it's the derivative of the exponent, which is 3x squared, and then e to the x cubed, not plus c. The plus c is gone because it's a constant. So that would be the derivative if we just left it alone. And it's really close to what we need here. But I want it to be a 2x squared. So the x squared part is good. We just need this 3 to turn into a 2. So to make a 3 turn into a 2, you would need to divide by 3 and multiply by 2. So these 3's would cancel. And then you would have that 2 out in front. Do you see how the construction of these kind of works? It's kind of fun, right? It's kind of fun, just kind of thinking backwards and thinking about what would need to happen. Now, down here, this one kind of looks like ln x, but it's like not quite there, right? But we know with ln, if you're taking the derivative of ln of whatever stuff is on the inside, that this derivative is the derivative of the inside over the inside, right? We know that that's how that works. So maybe what we could start with here is ln, and then we'll do absolute values because we know that the absolute values have to go in there with the antiderivatives of 1 minus 3x. So that would give it to us in the denominator, plus c. So if I take this guy and I'm taking his derivative, this would give me the derivative of the inside is negative 3 over 1 minus 3x. But I want this to be a positive 1 up here. So I know this is going to have to have a negative out front. Right? I need to have a negative out front because I need this to be a negative 3. I need it to be a positive 1. So negative, negative, those would cancel. And then to get the 3 to cancel, we would need to multiply by, it would have to be negative 1/3 because the negatives would cancel and then the 3's would cancel. So this would be negative 1/3 ln of absolute value, 1 minus 3x plus c. For this very last one, again, just kind of problem solving here. We know with the trig functions that the inside ends up staying the same, and we know that the function whose derivative gives us cosine would be sine, right? So we know it has to have a sine x squared minus 5 involved because the inside has to stay the same. And if we take this guy's derivative, it's the derivative of the inside, so that's 2x. And then sine's derivative is positive cosine. And look at that. That's actually already done. So we don't even have to change it. So that is our first part of our intro to antiderivatives. Any questions, comments, concerns on these problems? Like I said, you're going to get rules. So like you're not doing this problem solving thing very frequently. We're going to get rules that will allow us to do, especially ones like this guy and this guy, a lot faster without worrying about trying to problem solve our way through it. But I think it's important to think about where they come from so that when you learn the rules, you're not thinking that the rules are just kind of hogwash. Right? If there's no question, I'm going to go ahead and go to the next page. So this page gives you a bunch of just rules. So the basic rules here, if you have a function who's multiplied by a constant, when you take the antiderivative, the constant can just stay out front. If you have just a constant, so like, for instance, let me scroll over here. If you have a function and the original function, not the original, the derivative, erase. If the derivative is, let's say, 2, then the original function, which is the antiderivative, would be 2x plus c. So that's all this is saying, is that when you take the derivative of something like 2x, 3x, 5x, negative 5x plus a constant, that its derivative just becomes 2. So the antiderivative of a constant is just an x added onto it. The 1 over x rule, that's ln absolute value x. These guys right in here. The one that might need some explaining here is this x to the n one. So this x to the n one, and this works as long as n's not equal to, that's wrong. This should say not, it should say n not equal to -1, n not equal to -1. The reason that it doesn't work for -1 is -1 is this case right here. -1 is the only case where that doesn't work. The only case where it doesn't work is if n is equal to -1, then it's an ln absolute value x. So do make sure to circle that. So the way that this one is written here, if you think about, like, we had x cubed and his antiderivative was 1, or do we have x squared? Which one? I'm trying to think of. Oh, we have x. Oh, here it is. We had x squared. We had x squared, and his antiderivative was 1/3 x cubed. 1/3 x cubed is the same thing as x cubed over 3. And it doesn't matter which of these ways that you write it. So what this is saying is when you're taking the antiderivative of just something that would, like some power rule type situation, you add 1 to the exponent, and then you divide by that same number. So x to the cube, x cubed over 3 starts from x squared because you're adding 1 to the exponent and then dividing by the same number. But you can write it as 1/3 x cubed, or you can write it as x cubed over 3. Those are the same notation. They're different notations, but same concept. The other hard one to remember, you may have gotten used to sine's derivative being positive and cosine's derivative being negative. Now they get swapped. So in the reverse direction, cosine's antiderivative is positive and sine's antiderivative is negative. That one takes some getting used to. So let's go down here and work on some of these problems. So we have 4e to the x, and we know that if there's a constant out front, that in its antiderivative, we'll use the capital letter for the antiderivative, that the constant can stay there. And then e to the x, his antiderivative is just e to the x. For the next part, once again, this constant right here can stay here, and you'll see why in a second. -5, and then we can just do the antiderivative of x squared. So using this formula, the antiderivative of x squared, you add 1 to the exponent. So this is 2 plus 1. Maybe I'll write it as 2 plus 1 for a second, just so you can kind of see it in action. Over 2 plus 1. So I'll erase it now and put 3, just writing it there for a second so you can see it. X cubed over 3. Minus sine's antiderivative is negative cosine, so minus negative cosine x. And then there's always a plus c at the end. So rewriting this, we could rewrite this as 5/3, so minus 5/3 x cubed plus cosine x plus c. And we can always check. We can check to make sure that when we take the derivative of our antiderivative that we get back this function here. So I'm going to look at this guy. I'm going to take this guy's derivative. If I take it, I get 4e to the x minus the 3 would come down and cancel with the denominator. So 5x squared, cosine's derivative is negative sine x, and then the constant's derivative is 0. So this is the same thing as our original g of x. So once again, as a note with this guy right here, if you don't like this notation, your other option is x to the n. His antiderivative is the same thing as 1 over n plus 1, x to the n plus 1. So if I just kind of do a bunch of them, like if I have x to the 4th, this would be 1/5 x to the 5th. If I have x to the 6th, this would be 1/7 x to the 7th. If you have x to the -2, be careful. -2 plus 1 is -1. So 1 over -1, x to the -1. You can write it like this, or you can write it like this. So you can choose to use this notation or this notation, and it's the same thing. So this is the same thing as x to the 5th over 5. This is the same thing as x to the 7th over 7. This is the same thing as x to the -1 over -1, which is also the same thing as negative x to the -1. So those notations are different, but they're the same answer. So whichever one you like, if you like the fraction out front, then keep the fraction out front. If you like the fraction where it's underneath the variable, that's totally fine too. For part B, I'm going to get you started on part B and then give you a moment to try part B. So to get started with part B, you're going to simplify this thing first by distributing this denominator to everybody. So you're going to distribute the denominator to everybody, and then you're going to simplify. Distribute the denominator to everybody and simplify. And as a hint, the cubed root of t is the same thing as t raised to the 1/3 power. So I want you to distribute the denominator to everybody, simplify, then use the rules above to find the antiderivative. Once again, distribute the denominator to everybody, simplify, then use the rules to find the antiderivative. I'm going to give you like, let's say 3 minutes. All right, so let's go ahead and do this one. So simplifying this, we have 4t to the 5th over t plus 2t over t plus 1 over t minus t to the 1/3 over t. Simplifying that, we get 4t to the 4th plus 2 plus 1 over t. I'm going to leave him alone. And then minus this guy right here gets simplified to t to the 1/3 minus 1. So it's t to the -2/3. So I will be using this function here. This is not my antiderivative, by the way. This is not the antiderivative. This is just the original function. I'm using this original function to find the antiderivative, big P of t. This is a big P, capital P, the antiderivative. So we have a 4 out front, and then we're taking the exponent, adding 1 to it, depending on what notation you want to use. If you want to use the one that we did right here, you can do that, or you can do this notation over here. Maybe I'll do it the other way just to give you some variety. So adding 1 to the exponent, we get 5. So this would be 1/5 x to the 5th. If you have a constant, all you're doing is adding on a variable to it. So the 2 becomes a 2t. 1 over t, that's ln, so it's ln absolute value of t, minus, now adding 1 to 2/3, you get 1 over, so -2/3 plus 1 is 1/3. 1 over 1/3, and then t to the 1/3. plus c. This can be rewritten a tiny bit. So we have 4/5 x to the 5th plus 2t plus ln absolute value of t. 1/1/3 is actually just 3. So this is 3t to the 1/3 plus c. And we can check that by taking the derivative. So 4/5 times 5, that's going to be 4. Oops, let's write this as p prime of t. So this would be 4x to the 4th plus 2 plus 1/t minus t to the negative 2/3. And that is the same as this one right here. So that is the correct antiderivative. How did that one go? Good, good. Excellent, excellent. So it just takes some getting used to. The way that my brain likes to do these ones, I don't write down this intermediate step very frequently. Sometimes I will, especially with fractions, sometimes that's really useful. But oftentimes what my brain does when I'm taking antiderivatives is I'm adding 1 to the exponent and then dividing the number in front by that same number. So when I'm going from here to here, what my brain is doing is, okay, so it should be a 5. So 4 divided by 5, that doesn't simplify. That's just 4/5. Here with the 5x squared, add 1 to the exponent, so it's a 3. 5 divided by 3 doesn't simplify, so you have a 5 divided by 3. So that's the way that my brain likes to go through those ones. Add 1 to the exponent, then divide the number out front by that number that you put in the exponent. I'm going to skip this challenge problem, but I will say if you want to try this challenge problem out, something to keep in mind, if you want to try on your own time, is that sine squared plus cosine squared equals 1. And you can do some fun tricks with that to get the answer to this one. But I'm going to skip this one for now. So I want to talk about differential equations. So differential equations, there's a whole class of just dedicated to differential equations. We don't get into the nitty-gritty stuff that you would in a differential equations class, but we get into some minor differential equations. Minor differential equations. Essentially, differential equations, they're looking at stuff where you have, very simplify, f prime of x is equal to stuff with x, or y double or triple prime is equal to stuff with x, and you're looking for general solutions to these problems where you're given some information. Differential equations, and let me just be clear, differential equations is a really fun class. It's just, it really is specific. You look at very, very specific things. And it takes this one topic and it makes it much bigger. It's a lot of fun because you get to kind of narrow in on that. So in our case, what we're going to do is we're not going to deal with the very difficult stuff with differential equations. What we're going to deal with is we have a little bit of information about the original equation, or somewhere along the line we have some information about one of the equations, and we use it to figure out what the original is. So we're essentially solving for C. When these situations where we had to C, you can actually put a number in for C if you have more information. When you're given information like this, like you have a derivative and you want to find the antiderivative, and they give you information, we call that an initial condition. So they're giving you initial condition information, information about the initial condition of the original function. So here's how it works. You're just going to take the antiderivative like normal, and then you're going to use the information you have. So if we have a derivative and we want to find the antiderivative, we're just using our rules to find the antiderivative. So here, this one, 3, and then add 1 to the exponent, so that's going to be 3, so 1/3 x cubed. And like I said, in my head when I'm doing this, I would just divide 3 by 3, get 1, and just be done with it. But I like to put all the steps out there when I'm first starting to do these. Plus 4, add 1 to the exponent, so that'd be a 2, so 1/2 x squared. Minus 5, and if it's just an x in the denominator, then it's ln absolute value x plus c. Simplifying it, this is x cubed plus 2x squared minus 5 ln absolute value x plus c. Now we have an initial condition we can plug in, and that'll give us information to solve for c. So we know that f of 1 is equal to 17. Right? So 17 is equal to plugging in 1 to the equation. So plugging in 1 to this equation here. Or I guess we could put the 17 at the end to keep that kind of consistent. Plugging in 1, we have 1 cubed plus 2 times 1 squared minus 5 times ln of 1 plus c is equal to 17. So this is 1 plus 2. ln of 1 is 0, so minus 5 times 0 plus c equals 17. Right? 3 plus c equals 17. C is equal to 14. So we have all the information now. We can take this c and plug it in for this c up here. So your final answer of what f of x is equal to x cubed plus 2x squared minus 5 ln absolute value of x plus 14. So you don't have a plus c anymore. You have information about that original equation, so you're able to plug in that c value. So let's try it with a different one. Here we're given y double prime. So we can, if we find the antiderivative of y double prime, the antiderivative of y double prime is just y prime. So y prime, we know the antiderivative of sine is negative cosine x plus c. And we were given an initial condition here, if you look. They says y prime of 0 is equal to 1. So plugging in 0, you have negative cosine of 0 plus c is equal to 1. Negative cosine of 0 is just negative 1 plus c equals 1. So you'll get c equal to 2. So y prime is negative cosine x plus 2. Then you're going to the next layer. So you're taking the antiderivative of y prime, which would give you y. So I'm using this function right here that I already have and taking the antiderivative. So the antiderivative of cosine is positive sine. So sine x. Antiderivative of 2 is 2x, and then plus c. I have information about y that was given to me. Y of 0 is equal to 6. So plugging in 0 for x, negative sine of 0 plus 2 times 0 plus c is equal to 6. Sine of 0 is 0. 2 times 0 is 0. So this just comes down to c is equal to 6. So you have your final answer. Y is equal to negative sine x plus 2x plus 6. So with these initial condition ones, you're just finding the antiderivative. Once you've found the antiderivative, you plug in information so that you can solve for the c value. There are some really fun problems you can do with this involving, in particular, physics. And I think on the, we have some physics problems here. There's nothing on this page. Yeah, so there's some physics problems here. We'll do that. We're going to do this last one that's on here on Wednesday, as well as this physics application. And then we will do some reviewing for exam 3. And then it'll be exam 3 time. So if you have any questions, I will stick around to answer any questions you have. Otherwise, have a fantastic Monday, and I will see you guys all on Wednesday. Maybe I'll go back to this page so you can look at it longer if you need to. Bye.